Good afternoon, teacher. This is the presentation CPU metrics for my team with the member Janko and Soon Carol. For our table of content, we are divided into 6 parts: Linux CPU metrics, system time, idle time, user time, nice time, and wait time. So first, we will have to get to know the Linux CPU metrics first. So here on our slide here, you can see that when we run the command top-d1, it will show the current processes that is being run right now. And it will show the CPU message, memory message, but what we are focusing on today is the CPU metrics. There are 5 of them: US, which stands for user time; SY, system time; ID, idle time; NI stands for the nice time, and right here it should have been WA, which is wait time. Now, how they calculate this time is they calculate based on ticks. A CPU will have an amount of ticks per second. It could be a few tens of thousands, hundreds of thousand ticks that it will measure. It's like hertz, how many times per second it is. And it will count those times spent doing the process and find the percentage of it. So all of the 5 process, when you add it back together, is always 100. Now, to give a short summary of what it is, user time is you spend the normal user app such as browser or game. System time is handling file I/O, managing memory. For idle time is when your CPU does nothing. For nice time is when it's been running user process with a modified priority. And wait time is when the CPU wait for something to finish. Okay, so for our system time, so the CPU cycles spent in kernel mode, such as syscall, interrupt handler, I/O coordination. System time are most spent doing accessing the hardware resource like peripheral device or the writing, updating files, file I/O. So to show that we can increase that the system time does what it's supposed to do, we have this command here that will create 10,000 files while also deleting 10,000 files. Since creating and deleting files require a lot of system time, it is the best to show the process is going. And as for idle time, is the measure to about when the CPU is not being used with nothing to run. So first, we have to observe where we have to look for first. So up here is where the CPU matrix is being shown, the user time, the system time, the idle time. Nice time as well, and this is wait time. And this is where you can see all the process that is currently run, where S stands for the system process and I stands for idle. So for the first part, I will demonstrate that by running this command, which is to create 10,000 files and deleting them, we will trigger an increase in system time. As soon as I press it, it jumped up to 13.4. And you can see here, a bash command I run in the terminal has pushed the CPU percentage to 15%. And as it is done, the process got terminated and it's not there anymore. And as soon as it's finished, the system time got dropped back to 0.5 and hover around there. And as you can see, when there is nothing being opened, the idle time is near 100%. From this point on, Carol will explain the next part.
Hello. So I will continue from where what left off with user time. So what is user time? User time is another form of matrix. Similar, actually, it's complementary to system time, where it also tracks processes that are running in user space. with doing basic CPU calculation, accessing RAM, but most importantly, it's not accessing any important kernel privileges like system call, interrupts, or even dealing with I/O devices. It focuses entirely around how a process consumes resources purely based on CPU resource. And as you can see here, the way we can trigger user time to rise is by wasting CPU cycles by running a for loop iteration command for 1 billion or maybe a few hundred or few million times, so that the CPU gets used, the process is running, and when it's done, it will echo done. Moving on, we can talk about nice time. The thing about nice time is it's like a priority metric where a process will get its resource when a higher priority process which has lower nice values finish and no longer need resource to complete their task. As you can see here, we can trigger it by determining a process nice value to be 19. The lower the value, the more prioritized the process, with the most priority being the negative value. The default value is 0 for normal user process like the first one. And we will trigger a second one to represent the process running with nice value attached. Here I ran a top render of only the two process ID, and as you can see here, technically here it's not really an order by nice value, but in theory, processes with nice value above 0, the higher, the less prioritized it is. So that means that in the scenario where the system ran out of resource, or at least cannot spare any more resource, these processes will not be able to finish or even run at all, as a higher prioritized process would have to run and finish first. As you can see here, all we need is just to run and determine the nice value to be 19. Moving on to the last, wait time. So wait time is a metric that we use to measure processes that are waiting for data from I/O devices. That's how we define whether a process is waiting or not. If a process is currently doing some calculation or processing with the CPU, it's actually not waiting. But if it's like waiting for the network to give it data or the disk to give it data and it cannot do anything until it gets those data, then we can actually say it's waiting. And funnily enough, we can force the system to go into intensive mode by running the same command as the first system time multiple times actually, so that then we will see the system starts to slow down and waiting time increases. This is more likely because it's competing for resources and the system might crash, but if we run it just enough, we can see that waiting time will increase. So now we will move on to the demonstration. As you can see, we are in the virtual machine now. So what I'll do is to open top with the character with -d flag, and it will show the processes updating every 1 second. Now I will run the first command that will affect user time for the for loop. So here I will run bash-c. Now, in theory, the moment I run this, actually I need a n at the end to run in the background. In theory, US metric will spike and idling will dip. So the process is 1941. 1941 is using 100% of CPU usage, and US is actually spiking to 6.5, 6.7. I'll kill the process so that it doesn't eat any more resource. So now we will run the same command as before to show nice time. And I will run it once and then I'll run it another time. Oopsie, sorry. A nice dash n 19, the maximum value. So now when I'll do, it actually runs and we'll see that nice time metric is actually rising. Okay, so now for waiting time, what I'll do is to run the command that bot ran for the first demonstration, which is for I maybe I can add a few more. There we go. As you can see, because of that, waiting time actually flickers. And that's pretty much it for all the CPU matrices in Linux. Thank you.